Hello everyone. In today's lecture, we will be discussing the stability of the system based on the equilibrium point of the nonlinear system, and also we'll study how we can analyze the system around the equilibrium point. So first topic is stability of the system. So first, going to the mathematical part, let's define what is stability. So a system is stable if with the bounded input the system yields bounded output, then we can say system is stable. The system will be unstable for the bounded input if the output is unbounded. If the output is unbounded. What does it mean? For example, we have system here, system, and we have bounded input, and the output, if it is also bounded, then we can say system is stable. If output is unbounded, system is unstable. So this is how we can define the stability in broad sense. That's another definition we can have. The system will be stable with zero or non-zero initial condition if the resulting state trajectory tends towards the origin. So it means the system will be stable if it is if the resulting output or trajectories tends to the equilibrium point. So here we can say origin the equilibrium point, for example, x equal to 0. So as we have discussed in the last lecture, even the system does not have equilibrium point 0, we can make it 0 if you change the system, if you map the system to different domain. And there we can make the system in such a way that the equilibrium point will be 0, right? And if unstable, or we can write, it is unstable if the resulting trajectory tends to infinity. So if the resulting output is diverging, for example, if the resulting output is This is a system. This is system, for example, and this is the input for, and we are simulating this system with some initial conditions, and if the resulting output, for example, is diverging, then we can say x of t, for example, this is the time axis, and if with time, if xt is going to infinity over time, then we can say system is unstable. Now, let's assume we have a system x dot equal to f of x. This is, let's assume, autonomous system. Autonomous system means the system does not depend on time. And let's assume x star be the equilibrium point, and x is the current state of the system. If for all t, if x is always close to the x star, then we can say system is stable. Now, let's formalize the notion of stability in terms of some theorem. So there are different ways to define the stability. So let's come up some concept. It is called Lyapunov stability. So here, let us, or you can write, there is different ways you can define the stability, and one of them is Lyapunov stability. So Lyapunov stability. Let us consider the system be x dot equal to f of xt, for example, and let us assume x equal to 0 is an equilibrium point of this system, and also let's assume this equilibrium point x equal to 0 at time t equal to t naught. Okay. Now we have different definition for this system, how it will be stable in different conditions. So first definition is, this is very important in nonlinear controlled synthesis. The equilibrium point x equal to 0 is stable if for any epsilon greater than 0 and delta greater than 0. We are defining two different boundaries, epsilon and delta, can be found that such that the norm of initial value of x with starting inside delta implies that the value of x t will be always inside the epsilon for all t greater than t naught. So I'll explain what is this actually, this definition. So let's assume we have, this is the x-axis, x of t, and this is t. And this is also, let's take it like this. Now, we are defining two regions. One region is, for example, delta, and another region we are defining as epsilon, for example. Similarly, minus delta, this is minus delta, and this is minus epsilon. Okay. Now, if the system, if you look the definition, if the initial value of x starting somewhere here, for example, it is here, starting here, and over time, it is starting, for example, here, and over time, it will not cross the epsilon, it will be always inside the upper region, which is less than epsilon. The response of the system will be in this region. It will start from less than delta's value region, and it will not cross the epsilon region. Then this system we can say stable. So you can write this is stable. Okay, I hope it is clear. And if this condition, if the above condition does not satisfy or fulfill, the system will be unstable. So this is how we can define the stability of the system. Now, another point, it is asymptotic stable, asymptotic stability. This is very, very important. Here, if the system is stable and delta greater than 0 can be chosen such that the initial value of xt naught should start in the same region as the stable condition, but implies, if it is asymptotic stability, implies that limit t tends to infinity, x of t goes to 0. So what does it mean? So here the system should start in this condition, but over time the response should, it can start like whatever it start, but over time it will go to 0. So what this is mean, as t tends to infinity, the system should go to 0. This is how we can define asymptotic stability. Now we have another condition, third, globally asymptotically stable. Globally asymptotically stable. So here the condition is, if it is stable, of course it will be stable, and limit t tends to infinity, x of t goes to 0 for all x t naught. So it can start anywhere in the space, it can start anywhere, maybe if it's starting like this, but over time it will go to 0. So this is, we can say this is basically, it can start, instead of this, it can start here also. I mean, outside also epsilon. Doesn't matter where it's starting for all xt naught. So this is asymptotic stable system. Asymptotically stable system. And this is no, it is asymptotically global. It is globally, this should be globally asymptotic system. And this color is see. So this is how we can define the stability of the system, and also we can define how we can comment the system is stable or not. Also whether the system is globally asymptotically stable or it is asymptotically stable only. So these are the important points while we'll be discussing the Lyapunov stability based on the energy function. These are very important terms. Now we'll go to very important part, how we can analyze the system, nonlinear system, through a trajectory, through the state trajectory concept. So first, so before you move to that concept, first, in this nonlinear control concept, we'll analyze the system. Their system is nonlinear system. Based on the two Lyapunov methods. So Lyapunov first method, we'll explain in detail. First method and second Lyapunov second method. So we'll go through this concept in detail with example. And before we proceed to this part, first let's analyze and classification of the singular points. So here, let us define some important topic: analysis and classification of singular points. These singular points also you can call equilibrium points. Equilibrium points for a second order system. So this is very, very important, this topic. So here basically in this part, we studied how we can define the stability of the system, how we can define the equilibrium point, whether it's stable or not, based on these conditions. And now we'll analyze the system, nonlinear system. How can analyze whether it's stable or not? So these are the tools we are going to discuss. So let's assume we have a system x dot equal to f of x, and let's assume this is our autonomous system. And if you linearize the system, we can write the linearized system of this. I'm not going to detail of it. We have done this thing multiple times in our first course. But in the maybe next, after a few lectures, we will come up with the full concept. But for the time being, let me define the linearized system like this, del x dot equal to dou f dou x at xc and delta x. So here xc, this is the equilibrium point, and dou f dou x, this is nothing but the Jacobian matrix. And how we get this condition? This is basically we use the Taylor series expansion, and we can get this linear form. But we'll come up the full details of it maybe after few lecture. So for the time being, let's assume this is the linearized system we are getting from the nonlinear system. So let's assume this is equation number 1 and this is 2. Okay. And let's consider this, as we mentioned, this is second order system we are going to consider, second order system. So for a second order system, let us define the linear system, what you are getting here, the second order linear system be defined as x1 dot x2 dot equal to a, b, c, d, and we have the state vector x1, x2. And let's define this equation number 3. So please don't follow the step. First, we have the nonlinear system, and we are finding the equilibrium point. Around the equilibrium point, we are linearizing system, and this linear system, if it is second order system, we are writing in this form as equation 3. So here, this is the state matrix, or sometimes system matrix we call. This is we have done. Now, based on this system, will come up very important points. So let me write, based on the nature of eigenvalues, the equilibrium point can be classified as this. First is node, second focus, third saddle point. So this is the terminology we use in the nonlinear system, because in nonlinear system we are going to handle multiple equilibrium points in 4 vortex. So how we can come up these 4 different conditions on the based on the equilibrium points. So let's go step by step. So don't forget the steps what I'm following: nonlinear system and linearized model, and we are assuming the linear model in this form, and based on the eigenvalues of the system matrix, we can define what kind of nature of the eigenvalues will be, and based on that we can define the equilibrium point, whether it is node, focus, stable point, or vortex. So to find the eigenvalues, we know to find the eigenvalues. So what are the process? Lambda I, or SI you can write lambda equal to 0. There I is the identity matrix, so we can put lambda 0, 0 lambda minus AB CD equal to 0. And from this we can write lambda minus A minus B minus C lambda minus D equal to 0. And from this we can write lambda square minus A plus D lambda plus AD minus BC equal to 0. And from this we can get two eigenvalues, lambda 1 and 2, which is A plus D plus minus A plus D square minus 4 AD minus BC divided by 2. And this is basically nothing but the quadratic solution. And this is the quadratic equation. Second order equation. Okay. So now it's very important. If you remember, we had some linear transformation concept, right? So now I'm not going to detail of it. So I'm writing here straight away. Now, if we apply a similarity transformation, also we got linear transformation, as x equal to mz. In the previous lectures, in the modern control part, we had here T matrix, right? So here we are assuming M to the linear transformation matrix. So here we are getting different domain. From this, I'm not going to the full steps. So here we are getting different system based on this transformation. So we are writing Z1 dot Z2 dot equal to lambda 1, 0 and lambda 2. Okay. And from this, we are having, so this is the state Z1 and Z2. So here we are having two dynamics. One is the Z1 dynamics, which is lambda 1 Z1, and Z2 dynamics Z. Okay. So here, let us define, this is equation number 4 and equation 5. Okay. So now divide equation 5 by equation 4, we can write dz2 divided by dz1, we can write lambda 2 z2 divided by lambda 1 z1. And from this equation, we can write dz2 divided by, sorry, this is very, very powerful things in the control synthesis. So here actually we are analyzing the system, whether the equilibrium point are stable or not. So then we'll start the control. Here actually we are doing all the analysis part, how we can analyze the nonlinear system. So after we wind up these things, once you get the conclusion whether the system is stable or not, we can go for designing the control. So Z2 equal to lambda 2 divided by lambda 1 dz1 z1. And upon integration, if you apply integration from both sides, get Z2 equal to, we can write lambda 2, lambda 1, ln Z1. And we are assuming the here. Okay. So if you, from this expression also you can write Z2 equal to Cz1 to the power lambda 2 divided by lambda 1, right? So here C is the constant, integral constant. into this. So here, if you notice carefully, we are coming up very nice form. Here we are having the state variable as well as eigenvalues into the system, into this equation, right? So now also we can define, this is, let us define this, the equation number 6. Okay. Or we can have another expression from these two equations, 4 and 5, or we can write, since the system are decoupled, we can solve individual equation and we can come up some close one. Let me do it. From equation 4, we can write Z1t equal to Z1 naught e to the power lambda 1t. And if we assume for this equation, if Z1 naught is the initial condition, and for this equation, let's assume Z to be the, this is the initial condition for the Z2, equation 5. And from equation 5, we can have Z2t, Z2 naught e to the power lambda 2t, right? So this is easy to solve because both the equations are decoupled. 4 and 5 equation are decoupled. We can find this equation, right? So from both equation, so here actually lambda 2 is not function of t. This is simply t multiplied with lambda 2. Now eliminating, so let us define this, the equation 7, and this is 8. Eliminating t from equation 7 and 8, we can write Z2t equal to Z2 naught divided by Z1 naught is 1 to the power lambda 2 minus, sorry, by lambda 1 into Z1 of t to the power lambda 2 by lambda 1. So if you notice carefully, this term is actually constant because it has the initial conditions and the lambda to lambda, right, these eigenvalues. So we can say this is the constant, and let's denote this is the C. Now from this equation we get the same form, Z2t equal to C Z1 t the lambda 2 divided by, so we are getting the same expression what we had in expression 6. This is another way to get this expression, and let us define this is 9. Now, okay, I think we are, yeah. So we'll define this these conditions. We are now ready to explain about the node, focus, saddle point, and vortex based on this equation. But since today time is up, so we'll continue in the next lecture from this part, how we can come up these 4 different conditions and how we can comment the nature of the equilibrium point, because this is a very important part for studying the nonlinear state system. Let's stop it here. Thank you.